All right, this is lecture 16. It's another lecture in the series on using entropy, chapter 6. We will review the balance of entropy for a closed system because that was seen in chapter 5, but it was rather difficult. And then we're going to move on to the entropy value for control volumes in open systems. So going from this part to that part of the lecture is exactly the same thing as we did in chapter 4, when we developed the equations for the enthalpy of open systems using the workflow theorem. We're going to have to do the same thing here with entropy. It's a little bit more subtle, but it will work the same way. All right, so let's start once again, with the entropy in closed systems. We have seen this before, but it is quite complicated. So when you have the change in entropy contained within a volume, a controlled volume over time, delta S. Capital S is an equation of state. That is the net amount of entropy transferred into the system across the boundary between the inlets and the outlets. So that would be all there would be to it if we're looking at energy. Not so at entropy, because in the case of entropy, you have an amount of entropy produced within the system over time by frictions and irreversibilities in the process. Now, if this were a reversible process, that would be zero. And then, of course, the change in entropy would be just the change in the entropy values at each of the states. But this is not the case. So we can say then that the entropy change, which is this equation of state, so it's a difference between two values, is the integral between 1 and 2 of the real change in heat over temperature across the boundaries. This is not, it cannot be defined as just an entropy in terms of changes of states, because there is always the second term, sigma. We can, of course, differentiate that equation and have an actual non-exact differential for heat and non-exact differential for sigma. So I review this again. If we have a closed system and we go from 1 to 2, entropy is defined at point 1. Entropy is defined at point 2 because these are equations of state. But let's go from 1 to 2 through an irreversible path, and then back from 2 to 1 through a reversible path, through the reversible path. So S2 minus S1 is the integral between 1 and 2 along the irreversible path plus sigma. And that means this is the equation I just differentiated in the previous graph. But now take two paths, one reversible and one irreversible. So here is my irreversible, just copy that. And then I have to add to this, so this is that comes from here. I have to add to this the change in entropy between 2 and 1 along the reversible path. Well, that sum has to be 0 because it's an equation of state. So across a cycle, you come back to the same value, the change is 0. That means that if we define this to be the actual S2 minus S1, we get to 0 automatically, but that means that the real entropy change in the process between 1 and 2, which is this, has to contain an additional term sigma, so that they come out in total to be 0. That's why we define this as the entropy, but only for the case where the system is reversible, internally reversible. Can you define this as function of an equation of state? The real case, it has to be compensated for by the irreversible losses. So that's what we write here. Now, let me show you how this works in a few examples to make sure that we have everything under control. Let's take a system here where we have a metal bar that starts at a high temperature, and we immerse it in water that starts at a low temperature. The heat will drain out of the metal bar and heat up the water so that both the metal bar starts at H and ends up at F, final state, and the water starts at C and ends up at F also, the same F, final state, because that's the equilibrium condition. We put this whole thing so that the control volume encompasses both, but is thermally isolated from outside. So there's no heat that crosses the boundary for the total system consisting of both water and metal. Well, from the in energy balance, we can calculate the temperature, the T final temperature. So MCCM T hot minus T cold, this is the internal energy that comes from the biome. And then MCCW T cold, well, T final minus T cold, that is the internal energy that comes from the water. Remember, both are incompressible, so internal energy is just mass times specific heat times temperature. And specific heat doesn't depend on whether you're constant volume or constant pressure, it's just a given value. So this can be solved for TF. Now, the solution for the entropy is a little more complicated. The change in entropy, so between the initial and the final state, is the heat that flows across the boundary. But bear in mind, the boundary is thermally insulated, so that heat across the boundary is zero, plus the irreversible entropy that is generated by the process. Well, since this is zero, delta Q is zero, that means that this change in entropy of the whole system is just purely the irreversible entropy. There's no entropy that comes from the process itself. So now one has to look a little bit at the solution for this. So I can write delta S, which is sigma, as the delta S of the two components, which is the metal and the water. We learned in the previous lesson that because this is the metal, the delta S is the mass, the specific heat, and the log of the temperatures. And here we have the mass, the specific heat, and the log of the temperatures. So this is final state for both, between the initial state here, which was hot, and the initial state here, which was cold. So this is a term that's smaller than 1. Therefore, the log is negative. This is a term that's larger than 1. So the log now is positive. The sum has to be positive. So this term is slightly negative, but that term has to be larger, has to be more positive than that is negative. And in fact, you can do that because you can solve this for T final as function of T hot, T cold, MWs and MMs, and you will see that that is true and that this is true. That's left as an exercise if you want to spend some time on algebra, but it's going to be trivial. I can do exactly the same thing when I expand gases. So let me take an initial state where I have a gas at the pressure P1 and the temperature Ti, and the gas at the pressure T2 and the temperature Ti. So P2 and P1 initially are different. These gases are separated by a partition. And then we will open the partition and we let the whole thing equilibrate at a pressure that's somewhere probably, maybe, between P1 and P2, and a temperature that's not necessarily equal to the temperature of the initial gases. So, energy balance, U is U1 and U2. Say that we have equal volumes and we have different pressures, so we have to write actually total U here. T final is T initial. Because of conservation of internal energy. So then final pressure, Pi Vi becomes M1 RTI, P2, so we use the ideal gas equation in these two. And then we use the ideal gas equation in here too. We solve for the final pressure, because you can just substitute, and you end up with P1 times the ratio of the volumes, and P2 times the ratio of the volumes. So that is fairly simple. Now, the entropy balance is much more complicated, because the entropy balance is the final minus the initial, which again is the change in heat across the boundary. Well, we assume that the whole thing is perfectly thermally insulated, so that delta Q is zero, so that the entire entropy balance is actually the irreversible entropy of mixing of the two gases. Well, that consists of the two gases, the change for gas 1 from here to here, and the change for gas 2 from here to here, which we had the equations for the ideal gases in the previous lesson, are the entropies at the reference temperatures minus m the ideal gas constant, and the ratio of the pressures. Well, these temperatures, final and initial, are equal. We had that for conservation of energy. So these two are the same, and these two are the same. They just cancel out. And you have delta S1 is minus M1R ln PF over PI, and the same for the two. And the entropy then is this, and it is again, the minus sign here comes from here. And it is again positive, which you can verify because you know the ratios from this equation here. You let that for your own pleasure, just substitute PF in here, and you'll see that it comes out positive. So that's what happens to the closed system. This is why we said that the change in entropy is the net amount of entropy transferred in or out of the system, which in both examples I gave before is actually 0, and then the irreversible entropy. Now, if we take that same thing and we take a time derivative of it, so now the rate of change instead of the change is the net amount of entropy transferred, is the flow of entropy in and out of the system, and then the amount becomes the production rate of the entropy within the system. So the differential form of that is to say that ds dt, or S dot, is the change in heat that comes across the boundaries, but these are the heat flows, and this then is the rate of production of irreversible entropy. Why? Because we're going to feed this rate equation into exactly the thing that we did when we worked with enthalpy and internal energy in an open system. So this is a carbon copy of what you had in the beginning of section 4, chapter 4. The rate of change of entropy contained within the control volume is the flow of entropy in and out of the system. So that is the entropy contained here and the entropy contained there. The flow of entropy, that is this term. This is the flow of entropy associated with the heat that comes in and out of the control volume. It's here. This is the entropy that comes in. This is the entropy that goes out. And this then is the irreversible entropy that's produced within this whole thing. So we now have a function that applies to open systems and control volumes. That's the equivalent of the equation we had for the enthalpy. Note that we don't have a PV term in this, so we don't have the equivalent of a workflow theorem. The entropy theorem is much more akin to the internal energy. So for an open system, I can write that. If I have a volume integral over the control volume, that is what this looks like, the change. If we have an entropy rate, this is across the cross sections of the pipes that let in and out. But then the entropy rate production, this is the flow of entropy, this is the flow of the entropy, and then this is the irreversible entropy that comes from the process itself. And I can write that equation in integral form here. Looks more complicated, but it's actually exactly the same physics. If we do this in steady state, remember conservation of mass, mass in equals mass out, conservation of energy, 0, is the heat within the control volume, work in control volume, mass times enthalpy plus kinetic plus potential, mass as enthalpy plus kinetic plus potential. If we take the previous equation and apply to entropy, it also balances. 0 is the entropy that flows across the boundaries of my control volume, the entropy that comes in with the mass that the stuff that comes in, the entropy that flows out with the mass of stuff that flows out, and then the rate of production of irreversible entropy in my control volume. So if I have one inlet, one outlet problem, I have this, it's the heat across the boundary. This is the entropy change between in and out. This is the rate of production of entropy, spontaneous production of entropy. I can solve that for change in entropy, but that's just the same equation as that, solved for entropy change. And that's it for today. Thank you.